Hi, here's a couple solutions to some of the homework problems from 16.4, actually one homework problem and one challenge problem to help you get excited for 16.5. So the first one we'll look at is number 31, and this one is in the homework. So our idea is to find the volume of the region between the graph f of xy equals 25 minus x squared minus y squared and the xy plane. Again, anytime we see volume, your first step to think is I have two ways to do this. Which way is easier? One is I can come up with the bounds of a double integral where I'm integrating this surface, which hopefully we all see is an upside down parabola or paraboloid, sorry. Shifted up at 25 upside down because of the negative, and I want the volume under that surface and above the xy plane. So that's a pretty straightforward double integral where I actually integrate this function, and then my bounds describe the region in the xy plane that I'm integrating over. The other option would be to do a triple integral of just dv, where all the bounds describe a solid. That seems less obvious here, so I would go with the double integral. So again, the first thing you always want is a sketch. So either it's given to you, you're going to sketch it by hand, or you're going to use some sort of graphing software so you know what's above and what's below. I'm above the xy plane. Here's my xy plane. This is a paraboloid. Up here would be z is 25, and this thing is going down. So if I want to know what that region R is, because I am limited by the xy plane, I essentially need to know what would be the equation of this circle in the xy plane. How can I figure that out? Well, the xy plane is where z equals 0. So this is going to be this kind of projection of this circle onto the xy plane should happen when I get z, right? So I'm going to get z, I'm moving, we have here z equals 25 minus x squared minus y squared. Let's just kind of reorganize stuff. I'm going to get, if I plug in with the xy plane, right? So this is my paraboloid, and the xy plane is z equals 0. So if I substitute 0 in for z, I'm going to get my cross section in xy is this circle of radius 5, right? X squared plus y squared would have to equal 25. So that's my region R. So now the next question, so I know that I'm setting up my integral to get my volume. I'm integrating just a double integral over region R, which is that circle, and I'm integrating under my surface. So I am integrating some function of f of x, y, dA. Now my second option, once I've decided which two methods I'm using to find the volume, is which two coordinate systems am I going to choose? Do I want to keep everything in terms of x, y, and use a rectangular coordinate system, or do I want to convert everything to polar? Well, my region is exactly a circle, which in rectangular coordinates looks like x squared plus y squared equals 25. In polar coordinates, that would simply be r equals 5. And my paraboloid, I can also substitute to make easier. So I'm going to use polar. Remembering in polar, y is going to be r sine theta. X is going to be r cosine theta, and our dA is now r dr d theta, where I can do the dr d theta in whichever order I want as long as I'm careful with my bounds. And I also have the relationship that x squared plus y squared equals r squared. I will star this one. That comes up a lot. This is going to be the substitution you want to be on the lookout for in various different forms, right? Doing some clever algebra to make things look like that. So let's first convert everything into polar. So if I'm going to convert things into polar, now my function, which I'm going to pull out a negative. If I factor out a negative, we get negative x squared plus y squared equals z. So now I can see a pretty direct substitution. So changing this into polar, I'm going to have 25 minus r squared equals z, right? Now I have rewritten z as a function of r theta. There's no theta in there because it doesn't depend on theta, meaning theta can take on any value from 0 to 2 pi, and my paraboloid, where I am on the surface of the paraboloid, only depends on the radius out. Anywhere from 0 to 2 pi, 25 minus r squared is going to give me my upside down paraboloid, right? Z is still my output variable. Great. So now I have this one. That's the actual surface in terms of polar. That's what I'm going to integrate, and now I'm going to need to think about my bounds, right? So it's going to be a double integral. I'm integrating this function, 25 minus r squared. My dA becomes r times, I'm going to do dr d theta, although other orders are certainly available. So let's not forget about this r, because we're going to have to distribute that before we start integrating. So now I want the bounds of my radius in polar. So remember, my cross section, now I'm going to be looking at, r and theta. So my cross section is a circle. I want a circle of radius 5. So the equation of this circle is radius 5. The radius is always equal to 5. And if I want everything inside the circle, then that means I'm starting at a radius of 0, and I want to include everything out to 5. So my radius is going to go between 0 and 5. And then I want the whole circle, means my rotation has to go between 0 and 2 pi. So now my bounds here for the radius would be 0 to 5, and theta would be 0 to 2 pi. So this is expressing in polar the volume under this surface, 25 minus r squared is going to be my upside down paraboloid, over this region. The region is circle radius 0 to 5, so everything inside the circle, with theta going all the way from 0 to 2 pi, so the entire circle. So this describes the same exact volume using this different coordinate system, which is much, much easier to integrate. At this point, I'm going to assume you guys could do the integration on your own. Just a reminder, make sure you distribute that r first and then start integrating. Let's look at another example. The second example, number 32, I did not assign for homework. I'm not going to do the whole thing. I'm going to set it up. This goes again to multiple different options we have for volume. So I can look at volume as a triple integral, where I'm just integrating dv, and then the bounds of integration, all three of them describe the solid I want the volume of. This is usually the most helpful if my volume is stuck in between two surfaces where neither of them are a plane that's horizontal. That's going to be the easiest way to do by describing the bounds. If I wanted to do this with a double integral, I would have to come up with a volume under a surface and above a horizontal plane. Let's look at what this volume looks like. And this same problem is going to come up in 16.5, where they're going to show you an alternative approach. So just so you start to understand why do we need so many different ways to do the same thing, because it just gives us an opportunity to solve so many different kinds of problems a lot easier. So this is my ice cream cone on the bottom, hemisphere on the top. Clearly, most ice cream cones are not perfect hemispheres, right? There's actually a whole sphere of ice cream, hopefully, unless you got cheated with it going into the bottom of the cone. But we're just kind of looking at the volume in between the top hump of the ice cream all the way through to the bottom of the cone. And we're assuming here that our ice cream scoop sits exactly on the cone, such that there is exactly one hemisphere of ice cream above the cone, and that the circumference of my ice cream scoop is exactly the same of the cone, right? So this is a pretty perfect ice cream scoop, but here's the idea. And my job is to find all the volume in between this surface, the hemisphere, and not a plane, but this surface, the cone. So I'm finding the volume in between two surfaces where neither of them are flat. So my two options, so my option one, if I wanted to do a double integral, I'm going to have to do two different things here. I'm going to have to take the volume, let's call this plane capital P. So I'm going to have to take double integral. I'm going to integrate my sphere, my hemisphere. So I'll write HS for hemisphere. And then I'm going to have my bounds here going above my plane, right, up to whatever my Z value is. And then, or, on the XY plane, right? And then this would just be dx dy. Z value is probably not the right way, right? So then my bounds, I'm integrating the actual hemisphere, and then I would look at my cross section of X and Y, and I would be describing the circle that is that plane, right? So that would be my dx and my dy. And that's how I would have to do it. How do I make sure it's the volume limited by that plane? Is I'm actually going to take that hemisphere and I'm going to subtract that plane. So my function becomes this hemisphere minus that plane, so that I only get the volume to that plane, not all the way down. That is only the volume in this first part. Plus, I have to add the volume from the plane to the cone, right? And again, that plane is not the XY plane. Plane to the cone. So the surface is going to be that plane minus the cone. And then I need to still come up with my dx and dy. So that looks really annoying. So that's one thing that's really annoying with the double integral. But if I wanted to use polar coordinates, that's kind of the only option to me right now. So polar coordinates also, that's my second question, is do I want rectangular or polar? Everything here is very circular. Rectangular looks horrifying. I'm going to be having to integrate with square roots. I'm going to have bounds that are square roots of functions. Whereas in polar, this becomes a lot simpler, right? In polar, I can substitute. We would get the 8 minus, right? 8 minus x squared minus y squared. Sorry, I can factor out the negative and get 8 minus r squared, making it a lot easier. And of course, that's still going to be in a square root for my hemisphere. And then in the other one, the cone, right? So our cone here was the square root of x squared plus y squared is equal to z, right? So now I'm going to get my cone being the square root. So the square root of x squared plus y squared becomes the square root of r squared, which is actually just r, right? So z equals r is actually going to be a cone. And that's something you'll actually look at in 16.5 when you start thinking about expanding these polar coordinates into a third dimension, right? So this gives me my cone, this gives me my hemisphere, but I still have this issue with the double integral that I still have to do two different integrals. One to get the volume under my hemisphere and above this plane where they intersect, and a second one to get the volume from this plane to the cone. Both of them being complicated because even though they're in between this flat plane, right, the plane parallel to XY plane, neither of them are actually the XY plane, so I have to actually change my integrand. That's pretty complicated. Versus if I consider a triple integral for my volume, that becomes a lot easier. So now again, the idea being the triple integral of just dv is going to give me the volume. Well, now I can describe this in z's. My z goes from the cone, which was the square root of x squared plus y squared, up to the hemisphere, which is the square root of 8 minus x squared minus y squared. And then I'm looking on the xz plane, like we've done in previous problems, from the bottom of my circle to the top of my circle. Right, so negative square root of 4 minus x squared to positive square root of 4 minus x squared. And then my x's would go from negative 2 to 2. So in this particular case, my differential would be in the order dz, dy, dx. So that's an easier setup, but that is nasty because we've got all these square roots. So the question is, can I still switch this to polar? Can I switch the x and y's in terms of polars and just leave z in terms of z? And the answer is going to be yes. That's in fact what we call cylindrical coordinates. Z stays in terms of z. That's what lets me take these circular coordinates and move them up and down with whatever z I want, but still describe the x's and y's in terms of r's and thetas. So my z would now go from r to the square root of 8 minus r, and my dr, my radius is going to go from, in this case, it would be 0 to 2, and theta going from 0 to 2 pi. And then I would be integrating from dz and then r dr d theta, which is going to be a much easier integral. So something to think about that you need to consider the easier setup, both in terms of, is it easier to set it up with a triple integral, which in this case it is, because then I have just one pretty basic integral, whereas with the double, I really have to do two different parts. And then the second part is what coordinate system makes the computation the easiest if you actually have to compute stuff, which in this case, it would be some version of polar with the z. In section 16.4, they are actually expecting you, if you want to try it and see what answer you get, so when we do it again in 16.5, you're convinced you get the same one, to do the two double integrals using the polar coordinates. So describing the volume under the hemisphere above this plane, and then below the plane, above this cone.